All right, so we're back looking at section 3.3, some of your sample homework problems. We're talking about the zeros of a polynomial. And we have this rule on number 9 called the rational zeros theorem that helps you find all the possible rational zeros. Now, it's important. Rational is only the ones that can be expressed as a fraction. So this method won't find any imaginary zeros or any irrational zeros, but it will find the rational ones, which is what they want us to do here. So it works for a lot of things. And it's also going to help you find any zeros that you could find by graphing. So you could also graph this to see where the zeros are on the x-axis. It can have at most 3 zeros. The degree of the polynomial determines how many solutions you're looking for. All right, so let's get going. You look at the last number, the constant, 35, and you list all the factors of 35, which would be 1, 5, 7, and 35. Anything that will go into 35 evenly. And you put that over the leading coefficient. In this case, that is a 1. So over 1, factors of 1, which is just 1 in this case. I hope we have another example that has more interesting factors, but here just 1. So when we divide by 1, it just gives us these numbers here. So that's answer B, the first answer. And it could be positive or negative. You'll notice it has a plus or minus because we don't know the sign of the zero. We just know to use these numbers, the positive or the negative. Then in the next question it says, now figure out which ones work. Choose the rational zeros. Well, we're choosing the ones that work, so then we're going to find how to factor it after that. So which ones work, in other words? So do synthetic division with your list of numbers. So it's not going to be this one. It can't be all of them. At most, it can only be 3. It's probably answer C or D. So I'm going to try 1 with synthetic division. And you remember, you take the coefficients of your polynomial, 1, negative 3, negative 33, and 35. And try to find a 0 remainder. Oh, there we found it. 0 remainder. 1 is a 0. I feel pretty sure it'd be answer D, but to 5 here. Again, that's from our list. We would be trying any of these numbers and looking for a 0 remainder. And there we found another one. And then lastly, I'll verify that 7 works. 0 remainder. So those are the 3 that work. So answer C in our case here. Then the last part says, now use that information to factor. Now this part should follow. If we understand what a 0 is and a factor is, it's just the opposite sign here. And completely factored will have all 3 parentheses. So -1, a +5, and a -7. Just the opposite signs of your 0 in factored form, because to find the solution, we set each factor equal to 0. When we solve those, it changes the sign of them. So the solution is always the opposite sign of it in factored form. All right, so that's number 9. Number 10. So no, we don't get to do one with more interesting factors, but that's okay. Number 10 says, for the polynomial function, find all of its zeros. Now, what's changed here, we've shifted gears on number 10, is it's already factored. It's in factored form. Now we're going to talk about repeated factors, like we know that this is x equals +5, so probably answer D there. Just from looking at that, the sign changes like we talked about on the last problem. If we set that equal to 0, it would make the solution +5. And then this exponent on the outside tells me that this factor is repeated 4 times. It's repeated x minus 5 times x minus 5 4 times. So that's called a multiplicity. It's accounted for 4 times. Then in this parenthesis, it's not repeated. It's just to the first, so there's no multiplicity on it. But it is a quadratic, so there's going to be 2 solutions to a quadratic. And it is going to be plus and minus square root of 3. The reason would be if we solve this part set equal to 0, the 3 would come across the line and give us a +3, but then we would need to square root to finish solving for x to the first, and that makes it plus or minus when you take the square root of each side and then square root of 3. So answer D there. If we're graphs, which is where all of this is leading, in 3.4 you want to graph these polynomials, we would know these are real x-intercepts. All those are real numbers, no i's on those, right? It's a little hard to graph square root of 3 because it's not going to be perfectly on a but it will be about 1.7. You could sort of estimate it on the graph. At positive 5. Those three values, it actually crosses the axis. All right, number 11, same question. And notice we have a leading coefficient of 3. But that does not give us a 0. Notice in answer D, it's trying to trick us and say -3. But there is no x on that, so there's no solution when it's just a number. It's just a leading coefficient that will affect if it's an up or down curve, or if it's skinny or wider, the stretch factor. So no variable, no 0. Okay? No accounting. It's not D. Then moving on, this gives us x is +1. So I can see any of those, but it's multiplicity 4. So maybe it's A, maybe it's C. So we change the sign. X equals 1, multiplicity of 4. Then in this parenthesis, if you set 9x plus 5 equal to 0, you're going to get a fraction answer. The 5 will move across and change its sign, but then you also need to divide by the 9. So that gives us x is -5/9. And it's just there once, so no multiplicity. Then lastly, the x squared minus 4 equal to 0. You can solve that by factoring or using the square root property on this one. Just square root both sides, plus and minus 2. And there's no multiplicity out here, right? It's just there once. There are two unique answers, +2, -2. So that takes us down to this answer C. We had the +1, multiplicity 4. That is absolutely repeated. Then we had the -5/9 from that, and positive and -2 from that. And if we were graphing, these are all actual points along the x-axis that we could see. We might not be able to see their multiplicities by checking our graph, so you'd still need this method that part to say. All right, let's see, number 12. Number 12, we're going to work backwards and actually find the polynomial of degree 3. So there's no big multiplicity there. It's degree 3 with real coefficients with these 3 zeros. And that's why I say there's no repeated zeros, because 1, 2, 3, degree 3 solutions. So that will look like x plus 3, x plus 1, and x minus 4. And that would be our polynomial if it had no leading coefficient. But like on the earlier example, we could have a 3 in front or a negative number in front that affects the shape of the graph, but not really where the zeros are. But we do have to account for that if this clue is given, and it is here. Some of your homework will give you that clue and some doesn't. If you don't see that clue, that means the lead coefficient's 1 and you don't have to worry about it. But here we do have it listed. So there's some number, and we'll call that number, the book likes the letter A for that. Just saving that spot, you can call it any variable that you want. But see, if you called it X, it's confusing because there's X's in the equation. So something else. It's some other, and it's going to be the lead coefficient. So maybe call it the LC. But leave a spot for that. And then this clue, f of -2 equals -30, helps us figure that out. This means f of x, that's the x value, equals this y value. So plug this in for x, all these x's, and plug -30 in over here for the y. That's the y. So we'll have -30 equals some unknown, I'm calling it A. Plug in x is -2 for all the x's, and then equation solve that. We can do that with a little arithmetic here. That would be 1, and that solves or reduces to -1 and -6. These are all multiplied together, so multiply that out. Gives us +6a equals -30. Sorry, I keep losing my screen there. Then divide by the value with the variable, dividing by 6, a little equation solving, and voila, there it is. So A is -5. So back up to the top here. Now we know f of x, or y, equals -5, x plus 3, x plus 1, x minus 4. Now you're not going to believe this, but then they expect you to simplify your answer completely, not in fact form, the whole thing multiplied out. So do not factor. That would be nice if we could just, that was a lot of hard work already, but they actually want it multiplied out in a standard polynomial form. Now, so how do you do that? These four things are multiplied together. So multiply in any order that you like. Just get everything multiplied together. I think I'll start here and FOIL these two. First, outer, inner, and last. We'll have some like terms, so let's reduce it to x squared minus 3x minus 4. Okay, that's done. Then I'm going to times it by x plus 3 and get that incorporated. And then the last thing I'm going to do is distribute the negative 5. I usually save the coefficient to the very end. Sometimes it's a fraction coefficient and you just don't want to complicate it, but it'll just make the numbers bigger to multiply, so I save it to the last. And that's optional, of course. This isn't exactly FOIL, but it is distributing this times all 3 and then this times all 3. Everything multiplied out. So that'll make x to the third, x times negative 3x, x times minus 4. Then distribute the 3. And combine any like terms. I see a negative 3x squared and a positive 3x squared that cancels. A minus 4x and a minus 9x will combine to be negative 13x and minus 12. So all of that reduced to this. Then I still need to distribute my negative 5. So my last step, distribute the negative 5. And that is the answer that we put in this blank on number 12. Negative 5x cubed, 65x plus 60 in final expanded form for a polynomial. All right. The next one, I won't go through the whole rigmarole there like I did before, but I'll show you how to set it up. Notice it says a lead coefficient of 1, so we're not going to have that figuring out A part. That helps us, but we have more zeros. We have a 0 of 3, and, oh, well, maybe not more zero, but we have complicated zeros because we imaginaries. A 0 of 3 will be x minus 3. A 0 of 5 plus I will be x quantity plus I. And then in this is that you know that there's a conjugate. If an imaginary, you always have to have its conjugate in the 5 minus I. Then say it. Then you would distribute out your minus in front of your imaginary. Make it minus 5 and minus I. Same thing here, minus 5 and plus I. And then, just like on the last one, you have to multiply all that together, yuck. So, FOIL and multiply. Foiling is really distributing. It's just a multiply method with a special, shortcut way to remember it with special letters. But it is just really distributing. It means take this times all 3, this times all 3. Or if you're multiplying these two together, which I think I would on this, because you'll get rid of some of the imaginaries. I think when you multiply it out with hitting some I squareds, you'll take this times all 3, this times all 3, this times all 3. Get that answer, and then you'll need to multiply it by the x minus 3. And we won't have any constant that we have to distribute again because it had a coefficient of 1. But that's the process that you'll need on that number 13. All right, so I think that's a good place to pause, and we'll pick back up in the next video.